Okay, whoa, why don't we go ahead and get going. Welcome to our Thursday research conference. And in addition to being here in person, there might be people out there watching it. And if you're watching it, since all of our high-powered faculty are sitting way in the back, it may seem like there's few people here. But Dr. McQueenie is going to tweet a picture to show that there is indeed a good audience here.
Indeed she will.
Anyways, welcome, and I'm happy to introduce today Dr. Stephen Wu, who's a member of our faculty and is working on an interesting project, and it's interesting beyond more the fact that I'm one of his collaborators on the project. And he's going to talk about his work in natural language processing and information retrieval techniques applied to patient data, which is something new for us at OHSU in terms of using real live patient data for informatics research. So Dr. Wu's an adjunct assistant professor. He also spent some time working locally for a company called Trapit. Prior to being at OHSU, he was at the Mayo Clinic, which, as many of you know, has developed a lot of great natural language processing tools over the years, including things that we're using in this project. And he has a PhD in computer science from the University of Minnesota Twin Cities, and also a bachelor's degree in electrical engineering from Duke. So let me turn it over to Stephen.
All right, thanks, Bill. Can you guys hear me? All right, cool. Really appreciate the introduction and the opportunity to share some of this research with you. And so what I'm going to be talking about today is patient-level search in EHR, electronic health record text, and using natural language processing. So the big picture here is basically we're looking for groups of patients. We're searching for groups of patients. For example, children under 10 years old with asthma. Now, I have a room of informaticians here, right? So what do I need to know, or what questions do I have, or how would I approach finding this cohort of patients from electronic health records? Anybody shout out any thoughts that come to your mind? What is that? Age? Okay, yeah, right. Age. It's in that query. Anybody else? Okay, I can't really hear. Speak up. What? Diagnosis codes. Okay, it's one way to find them. Great. Anybody else? One more. All right, okay. Well, I thought of a couple of things. Even when you're just looking at children, I mean, what population are these children from, right? And just like someone mentioned, you got to filter based on age. That's typically a metadata filter if you're getting stuff from a database. But when you're considering getting stuff from a database, which database are you talking about? How do you write that query? How do you subset the data in an appropriate way? These are all typical things that we're going to have to do if we're going to do informatics on a lot of data, right? And that's before you even get to the problem of asthma. So someone mentioned diagnosis codes back there. If you're looking for asthma, you might consider looking at ICD-9 codes. This is what we bill for. You've got asthma because you paid us for it, you know. So unfortunately, my collaborator, a clinical collaborator, did a study and did manual chart reviews. You can't see those numbers. The sensitivity is 30%. The positive predictive value is 57% for ICD-9 codes for this particular sample. So there's some evidence that for some kinds of cohorts that you're going to look for, just a simple diagnosis code is not going to serve you very well, right? So, okay, ICD-9 codes might not work in every situation. Why don't we look into clinical notes then? Let's find the information in clinical notes. Well, once you open up clinical notes, you have to say, well, what am I looking for in clinical notes? Maybe I'm looking for coughing and wheezing, whether they used an inhaler, whether they had some positive tests or not, that kind of stuff, right? Yada, yada, yada. But even beyond that, you have to consider, okay, if they were coughing, was it at nighttime? That's a different story. And, oh, by the way, when we talk about wheezing in the notes, a lot of times we're saying there's no rales or wheezing, so make sure you get that negation in there, right? So there's a lot of fine-grained semantic information that's in the text that you need to be able to figure out if you're going to really make good use of the text, right? So that's on one side of the spectrum, but at the other side of the spectrum, we're concerned on whether you experience these symptoms over a course of 3 or 4 weeks or more, right? So that evidence is in different clinical notes. So basically what we're seeing here is if we want to handle clinical notes, there's some additional challenges. And I believe that clinical notes are important because we are endowed with human language faculties that actually communicate very well what happened. And it's very difficult to just codify everything in a different way. So we want to look at clinical notes, but some of the challenges that we're going to face are granularity, is this granularity challenge, right? So you want to get that fine-grained semantic distinction, but at the same time, you want to search and aggregate across the whole patient level, all of the documents, all the different kinds of notes and data that we have for that kind of patient, right? Okay, so there's this granularity challenge, and so for that reason, I'm going to structure this talk in 2 sections, basically. The first one is we're going to look at patient-level cohort identification, and this is an information retrieval or IR approach to the problem of searching at the patient level. And then we're going to look at a classification-based way to look at this at a similar problem. And we'll actually look more specifically at the problem of how do you aggregate evidence from single documents up to the patient level. And that's going to be in a classification framework with hopeful applications back to the information retrieval. Okay, so let's start with patient-level cohort identification. The key assumption that we're going to make right here is down here at the bottom. Cohort identification, we're going to cast it as an information retrieval problem. In other words, we're going to try to retrieve patients and rank which patients match this cohort the best. Okay? So it's not obvious that you would treat cohort identification as an information retrieval problem, but that's the approach we're taking. And so the problem setting is basically that you have, say you have n patients in a population on the left here, and for each patient you have multiple records of EHR data, right? We're going to take those records, index them in a standard information retrieval kind of index, an inverted index. And here I'm showing you just basically a text index. Let's just index the notes themselves. And then in response to, I'm looking for this cohort of asthma patients, right? In response to this cohort query, we're going to try to retrieve from that index documents and then aggregate to patients which patients match that cohort the best, right? And what we're going to produce from there is a ranked list of patients that you see coming out of the right side of that box there. And then with that ranked list of patients, we're going to compare, did my ranked list of patients compare well with a manual chart review? You know, if somebody went through and read each of the records and said, you know, this is actually a good fit for the cohort or this is not a good fit for the cohort. Now, the stuff surrounding this task is going to be 2 parts of a grant that I have here with Bill as my collaborator, where we are putting together the evaluation framework. We're putting together some of the stuff around making this happen. So we're going to be actually we've pulled 100,000 OHSU patients from Oak Tree and gotten their electronic medical records since the implementation of EHRs here at OHSU. It's stored on a secure server, and then we're going to be defining 50 cohorts and finding basically manual chart reviews, relevance judgments, whether documents are a good match for these cohorts. And Tamara Timmons, who just joined us, is right over there. Talk to her; she's pretty awesome. She's going to be judging, creating these cohorts and judging them, so that we have a manual chart review to test our automatic chart review, which basically are search algorithms against. So this is in process right now. It's not done. It's part of a 5-year grant. And so what we're using preliminarily is the TREC medical records track data. And this is the Text Retrieval Conference. That's what TREC stands for. And actually, Bill helped put together this corpus, and Steve Bedrick, I think, also may have presented on this recently. But we have a bunch of documents from Pittsburgh, University of Pittsburgh, and there's 17,000 visits. They had to break it at the visit level, and there's multiple reports or documents per visit. And the idea is to retrieve visits that are relevant to cohorts. Now, future work would be patients, right? They had to cut at the visit level because of de-identification and that kind of stuff. In fact, in our local OHSU corpus that I was just talking about, it will be protected health information, and so we'll be able to keep all those linkages and look at actual whole patients. In the TREC medical records track data, we have 81 topics, and they're fairly simple text queries like patients who have been treated for vascular claudication surgically. And there were judgments that were done by Bill and Steve or the teams that they put together. Manual chart reviews to figure out whether documents and visits were relevant to cohorts. And we're going to compare our search techniques against that. Okay, so that's the problem set up. Here's what the methods that we use to actually do the search. And the general approach is called language modeling and information retrieval, language modeling IR. And the baseline model is the query likelihood model. It's really simple intuition. Basically, you think, I'm looking for this particular document. Here's the words and phrases that I think are likely in this document. I'm going to stick those in my query, and I'm going to write my query to find that document, right? So that's the intuition behind it. If you have a document that you're scoring for its relevance to a query, and then you're going to rank all the documents and say the best scores are the most relevant to those documents, then query likelihood does this. It uses the probability of the query given the document. That's basically just that intuition that I was describing earlier. You imagine the document and say, given that, what's the likelihood that I wrote this query? Okay. What this allows us to do is look at statistics. There are a lot of information retrieval approaches that previously used scores, very good approaches. But when we use statistics and cast things in the light of probabilities, we're able to make use of a lot of statistical reasoning and modeling and that kind of stuff. And that's why we call it statistical language modeling. And that's why this is called the language modeling information retrieval approach to information retrieval. Okay, so this query likelihood and language modeling in general actually do very well, just at a broad strokes. But there are some weaknesses. For example, the terms might have too coarse a granularity. Just like we were describing earlier, they might not get that fine-grained semantic distinction. Additionally, they might be incomplete. There might be other terms that could have supported what this term meant, but those are left out of a simple query. And there might be term dependence. Query likelihood doesn't actually even consider if you had two terms, what their relationship with each other, right? They just consider them as completely separate searches. So term dependence is another thing. So, okay, so I'm going to go through an approach to tackle each of these problems. The first one, layered language models, is something that I introduced. It's a contribution that tries to tackle coarse granularity. Mixtures of relevance models and Markov random fields are well-known techniques, and eventually I'm hoping to combine all of these. But what I'm going to do is go through each of these different techniques. I'm going to show you just a really broad view of the methods behind it, and then just the takeaways from some of the results for each one of those things, and then look at some of the future work that hopefully would bring this together. So, okay, we're looking at, again, want to tackle the problem of coarse granularity with layered language models. Okay, so basically, with a layered language model, you start with a text layer, right? This is the layer that's actually in your electronic health records. You look at clinical notes, and this is what you read: chief complaint, severe cough and fever. Cough started 2 days ago. No expectoration. And when you take that piece of text, you can do something beyond just looking at the piece of text. We run it through an information extraction pipeline, and actually there's a few of them that I use: MedTagger, CTakes, a few of them. That blue box there is named entity recognition. So out of that, you're going to get something like a concept that you've identified. Attribute discovery, you're going to find things like whether something is negated, whether a term is negated or not, or you're going to find the semantic group. Is this an anatomical site, or is this a sign or symptom? Okay. So once you run it through that kind of a pipeline, you can basically annotate the text and say, hey, I've got additional layers of information here, linguistic layers of information, and what this allows you to do is normalize for things like negation, and with these concepts, you can normalize between different ways of saying the same thing, right? So you've run this kind of algorithm, you've produced some output, and basically what we're going to try to do is search over both the text and those other kinds of output, right? So again, what I'm saying is that a language layer, is basically the output of one of these steps in the natural language processing or information retrieval, information extraction pipeline, and at each step's output, you have some output that you might be able to use in retrieval, and so this particular equation would be considering text and concepts and attributes sort of separately, and then just combining them together. I call that the split-layered language model. Okay, so this is probably the simplest kind of layered language model that you could have. So I'm going to give you some basic results on a split-layer language model. If you look over at the right, this is mean average precision. Those are the numbers that you're seeing here. And just a caution on some of the other charts. I'm going to show you a couple other numbers as well. Those are not comparable between the charts. The numbers are comparable within each of these tables. So basically, what we have here is the text. This is your baseline number. This is the baseline query likelihood model. You're just looking at text. You're just considering the text pieces separate from each other. You're not augmenting it with anything. You're not adding any other layers, and you get some kind of performance. Now, because we've looked in the text and found all these other layers of information, there's some temptation to say, hey, well, if we produced all these things from the text, can we use those instead of the text? You know, maybe we've codified things into this concept form, and that can actually replace the text. So that's this next line here, that concept form. And what we're actually going to see is that concepts cannot easily replace text. Maybe if you did some additional work, but it's not a simple prospect to just replace text. And additionally, if you look at adding negation and semantic groups and stuff like that to the text, that's that top box there. That also is harder. It's not an immediate thing for you to be able to improve performance just by saying, oh, now I know the semantic group, so that's good extra information, right? So it's not always more information is better. In that case, I believe it's because it's splitting the space, it's increasing the size of the vocabulary, and making your estimates of term frequencies and stuff like that a little less plausible. But I digress. Another thing that you can see on this chart is if you compare the second and third line with the fourth line, the fourth row, the fourth row where you're combining both text and concepts in the same model is statistically significantly outperforming the single layers every time. So what we get is, what we find is basically that at least the text space and this concept space, these are complementary representations, right? So these are, they have different kinds of semantics or different amounts of semantics that are perhaps overlapping but are complementary to each other. Okay, so these are split layer language models. Now I'm going to look at the problem of what if you have an incomplete query and you want to do some query expansion. So this is work that I did with an intern, Dongqing Zhu from University of Delaware, and so the way that I approached query expansion was mixtures of relevance models. Okay, so the basic idea here is, say you have n collections. You have your Pittsburgh natural language processing corpus, but maybe you have Wikipedia articles as well, or maybe you have a large web corpus or something as well. Maybe from those corpora we can find relevant terms that are, find things that are related to the query that I submitted, the query that, the asthma patients that I was interested in, or the vascular claudication patients that I was interested in. So the first thing you do is you search from each of those n collections, and in each of those n collections you keep the top documents. And within that set of top documents, you look at what are the best terms in these top documents, and you keep m of those terms from each of those collections, and then you weight the expansion terms. You score the original query. When you originally did that query and got that document list, you have a score. But then you also mix in a score of, well, how important is this particular possible expansion term within this corpus, right? So you mix in that kind of a weight, and then you combine the scores from each collection. Then you combine all of the terms across the query, and you get a final score. Now, a lot of people have done query expansion, and a lot of people have found mixed results with query expansion. I'd say the key here, the reason that this actually turns out to be a very, very helpful, empirically beneficial way to help information retrieval accuracy is because of this weighting. A lot of people don't do the weighting in a principled manner, and here we're doing weighting in the same probabilistic kind of framework that we were talking about earlier. Okay. So I'm going to jump to some results here again. And this test here is basically showing what happens if I add an expansion corpus. So I was talking about having n collections. I'm going to look for expansion terms in this collection, in that collection, and whatnot. So if I go from looking for things in one collection, like the target collection, PIT NLP, and then I say, hey, well, I'm not just going to look in that collection for expansion terms. I'm going to look in a large corpus of clinical notes. And we had a corpus of about 50, 60 million patient records at Mayo that we were using for this test. So when you look for expansion terms in that additional corpus, in addition to the original corpus, you are improving performance every time. There's the change in your map score and the p-value, so you can see that it's statistically significant. Even if you had 3 other corpora that you were doing query expansion based on, and you still added this one corpus, this Mayo Clinic corpus, you actually improve results regardless. Okay, so you might think that more data is better, especially more data that's in your domain is better. But that's not necessarily the case. This plot is a learning curve. And so on the x-axis here, you're seeing how many millions of unique terms exist in a corpus at a particular point. Okay, so what we're going to do is try to do query expansion with this proportion of this 50 million record corpus at Mayo, and this proportion, and see how does that increase over time. And in fact, what we find is that if you put together this learning curve, you find that more data is not necessarily more optimal. You see that the results level off and actually go down a little bit. So in fact, not using the whole Mayo corpus would have actually gotten us more optimal performance with mixtures of relevance models. So that's a pretty interesting result. But overall, this technique of mixing relevance models from multiple collections is very, very helpful. Okay. All right. I'm going to look at the third problem that we were talking about. Oh, we've got a question.
Yeah. So if you, because Mayo is so, I know what you're saying about how much of the data you add.
Yeah.
But I feel like Mayo might be the driver, right? So did you do the opposite of this, where you have Mayo and then you add the others?
Yeah, we actually have, in the JBI article, we have a comprehensive listing of 2 corpora, 3 corpora, and 4 corpora. Yeah. So, so what we do have, the 4 corpora, this result down here is actually the highest result that we had in the whole test. But we also did the power set of things.
It didn't matter if you, I guess, because you said Mayo is the largest, correct?
No, it's not. So ClueWeb is this humongous collection of web documents. That's the largest. It's like terabytes of data. And so, yeah, that's a really great point. Size is not the greatest factor. Perhaps the similarity of domains is possibly a greater factor. If you look at each of these expansion collections individually, Mayo is the top, followed by PIT NLP, which is the target collection itself. So that's kind of interesting because this large clinical corpus outperformed the target collection itself, but they're in the same domain. So that's important. And then genomics was next, and then ClueWeb. So the least, ClueWeb was the most general, and it was the least helpful, even despite its huge size. All right, so let's move on to term dependence. And this is a way to handle the problem of just considering the terms in your query as a bag of words, where they're not connected to each other and stuff like that. And so the query likelihood, if you had patients treated for vascular claudication surgically, you break it, smush it down into just 3 words. And the query likelihood model, you're basically independently searching for these 3 things and combining those scores. Right? The Markov random fields way to look at term dependence is there's 2 variants. One is sequential dependence, where basically you say, hey, I'm going to look at this phrase, vascular claudication and claudication surgery, and I'm also going to consider if I don't really care about their ordering of the terms. That's what sequential dependence is going to be. And there's also a full dependence model where on top of that, you add the relationship between things that are not necessarily neighboring. So you've got all 3 terms at once. You've got the first term, vascular, and surgery, the third term, at the same time. So that's a full dependence model. So both of these are Markov random field models. And the graphs that you see here basically embed the probabilistic assumptions that are being made. And when you implement something like this, it really turns out to be something quite as simple as this. You're just basically quoting stuff and giving them weights. But the probabilities that go behind the weighting and all that kind of stuff are some of the genius behind term dependencies. And it's not my genius. It's Metzler and Croft. But it's a really great model. And that's empirically true as well. These are learning curves. On the x-axis, you have a smoothing parameter. I won't go into what that is, but what you can see really clearly here is on the top, the text MRF, or Markov random fields model, is doing the best on its own as a single layer, right? But additionally, if, as I'm trying to do, you want to combine other layers of information, the text MRF model, this Markov random field model, also does the best when you combine it with other kinds of other layers of information. So basically, we have here a term dependency model that is very effective. And so in previous work, we've combined the term dependence model with the query expansion and stuff like that, there's going to be continued work in bringing these things together. So just to give you a little bit more definition on what I'm going to be working on in this grant, is I'm going to look at the methods behind this picture. We're going to be going through natural language processing to add those additional layers labeled content artifacts here. Additionally, aim 2 is going to be, hopefully we're going to add stuff that you're going to see in the second half of this talk. So hopefully the direction right now that we're working on is combining layers, term dependence, and query expansion. And then we'll look at this relational and temporal kind of search. Okay, so what you mostly saw in this whole section was how can we get into that kind of fine-grained stuff and bring it out and surface it so that we can find patients using that kind of information, right? What I'm going to look at now is patient-level temporal aggregation, and this is explicitly looking at how do you aggregate data that you got from one document versus from other documents for the same patient. Okay, so let's look again at that setting of pediatric asthma that we started out with. And maybe it's not, I think on my data set's not exactly less than 10 years, but it is children who have asthma. Now this is a problem from a clinical perspective because there's delayed diagnosis in 65% of cases with 3.3 years median delay, according to one study. And the ramifications of this, if you have not gotten a diagnosis of asthma, then you may be prevented from getting therapies like an H1N1 vaccine, or you may get unnecessary treatments because if you did have asthma, you can say, oh, it's just asthma, let's go here. Instead, you have to run a bunch of extra tests or something like that. This whole problem setting is something that my collaborator at Mayo Clinic has helped me define, and that I'm continuing to work with him on. So another interesting thing about looking at asthma, though, is because it's a chronic disease. We are interested also in associating time with the asthma status. Not only did they have asthma, but when did they get asthma? So looking at the data here in the problem setting, the data that we have is provided by my clinical collaborator at Mayo. There's 112 patients, fairly small sample set, but it's one that he had worked with before from Mayo Clinic. And we had a development set with very similar characteristics. And what we had was, for each of those patients, we did manual chart review using expert criteria. So these criteria had like main symptoms, they had the time course, did these symptoms recur? And then there were some other indicators that were additionally included. And for each patient, doing manual chart reviews on end documents. Okay, by doing those manual chart reviews, we're producing a patient-level gold standard where you're able to say, does the patient have asthma or not, yes or no? We're also producing an index date, and index date is the technical term that my collaborator uses, Young Jun. The index date is the first date that a patient could have been verified for having asthma, and we're able to infer per instance status from this. What I mean is hopefully clearer on this plot here. In this timeline, if you have a patient with asthma, then each of these X's along the line is an instance. It's like their document history or their natural history. So each time they came in and you saw a document, there's an X there. And we'll call that instances. That bar there is the index date. That's the date that this patient should have been considered to have asthma. And then overall, you have something saying that this patient does have asthma, right? Asthma status, yes. And the asterisks there mean that those are quantities that we're going to estimate. So we need to estimate whether a patient has asthma and when that patient got asthma. right? So now, if we consider a different instance, so consider that instance right there. That's before the patient should have been diagnosed for asthma. And so in that span, the asthma status was no, and the index date was none because they haven't gotten asthma yet, right? Make sense? Okay, so that's our data and the stuff that we have and the stuff that we're trying to estimate. And the way that we estimate it is, again, through a natural language processing algorithm, information retrieval producing 23 primary features for each document. And then we do a classification step using machine learning algorithms, decision trees, logistic regression. We also have a logic-based rules version where we're basically trying to write rules to recreate the way that they did the manual chart review. Okay, so and then you can compare the manual chart review versus what we produced, both for the accuracy, the asthma status, and for the timing. Okay, so now this is the interesting stuff. These are the methods of how can we combine these features over time. Okay, so again, you have the documents as X's, and you have the index date over there. But here, we're actually going to be, these shorter lines are bronchodilator use. Oh, here, I found this feature. I've discovered that, based on my NLP, that there's bronchodilator use in these documents, right? How can I aggregate this evidence to figure out whether I have asthma or not? And the OR method, the OR algorithm, is really the simplest algorithm possible. The first time that I see bronchodilator use, I'm going to say, "Hey, that's asthma," and we'll weight that against other features, but it's basically a unit step function, right? Okay. Another very, very simple way to do aggregation of evidence is just to sum the data. Okay. Every time that I've seen an example of bronchodilator use, increment and count up, right? And then try to determine at any given point, based on that counted up number, whether I have asthma or not. Okay. So those are two very simple methods for determining, for aggregating evidence over time. But there's also a probabilistic way to do this. And so, if you can't tell, I enjoy looking at probabilities and stuff like that. So what I did was estimate probability density functions. And the example that I have here is estimating the index date probability. Okay, so you don't have to look too much in detail at the equation. But if you look at this chart here, basically the 0, at time 0, that's when you observed a feature. Okay, so let's say you observed a feature of a methylcholine test at time 0, and you move back some number of days and see could the index date for asthma have been on this day? So in other words, what we're seeing for this methylcholine test, that blue line there, is that the index date, the date that patients usually are actually found to have asthma, occurs before you actually get the test, the methylcholine, right? So this is not necessarily a great predictive kind of feature. It's kind of like a response. It responds to already having asthma. On the other hand, bronchospasms are kind of the other side of the picture. You see that this is when the 0 is when the bronchospasm was found, and over here you see how likely is it that the index date occurred over here, right? So bronchospasms, the majority of the time, the index date or the beginning of asthma happens at or after you start having an episode of bronchospasm. Okay, so using these probability density functions, I can put these onto each instance of finding a particular feature in the data. So I'm using that exact probability density, that function that you saw before, estimated via kernel density estimation. And so if you can just imagine, like bronchodilator use, the curve for that here, and then another of the same curve for that here, and another of the same curve for that there. And at any given point, you're adding up the evidence from each of those curves. Okay, and so what you see in the green line is the sum algorithm that we just saw, but the purple line here, or is it blue, is the PDF-IN, which is the index date probability. Question? Okay, index date is the first date that a patient could have been considered to have asthma. So that's when in chart review, I'm reading this person's chart. They don't have asthma. They don't have asthma. Oh, they do have asthma. That's today. That's the index date. Anything forward, they are an asthmatic person. Does that make sense?
Based on a diagnosis?
That, based on manual chart review. So actually, it's based on that criteria. There's the three groups of criteria: the main symptom, the recurrence over time, and other factors. They're actually rigorously reviewing the patient records, and they have their own logic criteria for saying this is when a patient has asthma. Does that make sense? Okay. If there's further questions, we can take it offline. So this is the index date probability, and what you see it doing in this characteristic is that it says, hey, I've seen at each time that you have bronchodilator use, you're saying, hey, I think I've seen something that's really great evidence for asthma, that I should diagnose them today. But then as you go on with other records that don't have this kind of evidence, that assurance kind of fades away a little bit, goes down a little bit, until you see another example of that. So that's what's happening with this index date probability. But there's something wrong with this model, because what if you want to just know, do I have asthma right now? I don't really care if today is the date that I should be diagnosed for asthma. I just want to know if I have asthma today, right? So that's what this alternative probability density function is. I defined it a different way. We won't really go into detail on that equation. But basically, it's not saying, given that I've seen this feature, do I have, is today the date that I got asthma? Or instead I'm saying, do I have asthma today? And what that does is kind of the opposite of the previous for this particular feature. It basically says, well, you know, I had bronchodilator use, and even though I don't see bronchodilator use right now, the likelihood that I'm going to eventually be shown to be asthmatic is going to increase. Maybe another feature will come in and trigger that kind of thing. So this is the positive status probability, EFST. So when we evaluate, when I evaluated these aggregation methods, I had to consider different settings based on the statuses per patient. So here, for this particular patient, if we consider their whole patient history, their whole document history as one training sample, and say, hey, this patient has asthma, great. That's one sample. That's a single status per patient kind of setting, SSP. Now, on the other hand, like we said, if we looked at one of these previous instances, that was a negative instance for asthma, right? So perhaps you can look at a multiple statuses per patient setting. And each of these kind of has a different implication for when you're testing. The SSP setting, if you're testing on SSP, that's kind of like retrospective epidemiology, right? I'm looking at these records at this point in time. I'm going to look back into history and say, did they have a particular disease that I was interested in? And what we find is that the results here are mostly in this F1 column, the F1 score, and higher is better. We have the ICD-9 codes giving a really low value of 40%. These are the same numbers that we saw at the beginning of the talk. Basically, precision and recall weighted at the harmonic mean. And so 40% there with the ICD-9 codes, but with any of the aggregation methods, and even with the logic method, we are getting better accuracy in determining whether a patient has asthma as a whole, looking at it as a retrospective setting. Another thing to note on this plot here, on this table here, is that the sum algorithm actually does really, really well. That sum algorithm, it's just doing counts. It's very simple, but it gets very promising performance. And it's actually, there's a recent article in JAMIA by Hipsack. It's talking about sequence time and versus clock time and the parameterizations of time. This is sum basically allows you to look at sequence time, which is pretty interesting. But anyways, unfortunately, the OR algorithm didn't do very well, which basically tells us that if you're just flipping a switch, that's getting rid of a lot of information, right? You're losing some information that you could have used to help make your decision in time of, is this patient asthmatic or not? Another thing is if you try to train on multiple statuses per patient, you're kind of cheating because you have non-independent samples. Each patient is basically in the training pool many times, and because those are non-independent samples, the performance is fairly low. Now, if we look at multiple statuses per patient, MSP, then this is sort of like a clinical decision support setting. I came into the clinic today. I had a document written about me. Do I have asthma based on this information, right? Do I have it today? And overall, we see that this clinical decision support is a slightly harder setting because you're getting penalized if you're early or you're late to your diagnosis, right? Another thing that I found very pleasing with these results here is that the highest performance that we have in this kind of clinical decision support setting was with PDF-ST. And if you remember this particular probabilistic method, we're explicitly estimating the asthma status probability given the features, right? So this method is exactly designed for this kind of a setting, and it shows up in the results. So that's really nice. And we find again that even though you're testing on multiple statuses per patient, training on that is still too noisy because of this non-independence of the samples. And I mentioned that we can look at not just the accuracy, but we can also look at the timing of, we are also estimating the timing of when the index date was. And these are all of the different methods that were tested and how their timing fared. If you see the bar on the right in the middle of the graph, that's basically it was dead on within a month on either side of getting the index date correct. If you move to the left of either of the plots, then that's we diagnosed asthma before it should have been diagnosed, and if it's after, we diagnosed it after it should have been diagnosed. So this top left plot is ICD-9 codes. Again, a lot of the instances were missed. So that's that bar on the right there. And then if we look at just a regular logic-based method, or actually any of these methods, they outperform in terms of timing. They outperform ICD-9 codes. really interesting is this one, PDFIN, when we directly estimate the index date. So again, this probability distribution was designed to find the right index date, right? And so it actually does a really good job of that, and it interestingly does not really have any delayed diagnoses. It has some jumping the gun, trying to diagnose asthma before it actually happened, but it doesn't have any delayed diagnoses. These are missed cases over here on the right. So there's a lot of other interesting stuff that that I'm looking at for future. We're looking at other time points. What about if there's remission, relapse and remission of asthma? And what about other chronic diseases and stuff like that? And then how can you embed all this kind of stuff into an information retrieval framework, like the one that we were talking about earlier? And that would basically be aim 2 of the grant that we're working on here. So in conclusion, today what we've looked at is this granularity issue with looking at clinical text. You've got to get down into the fine-grained stuff with NLP, but you've also got to aggregate to the large level with, maybe this temporal kind of aggregation, also other kinds of aggregation in the information retrieval framework. Within information retrieval methods, we looked at layered language models and saw that some layers, like concepts, can improve performance. We're currently working on getting those various layers to work with query expansion and term dependence. And we're also building that large resource here at OHSU in order to evaluate all of these methods. And hopefully that resource will eventually be something that many others here at OHSU, and many of you perhaps, will be able to leapfrog off of, or springboard off of. Also, we've looked today at temporal aggregation. We've seen some interesting functions of ways that you can aggregate data. We've seen that the clinical decision support setting, where you're looking at every step of the way, might be a little bit harder than retrospective epidemiology. We saw that some of the results reflected the way that the probability distributions and the aggregation methods were designed. And there's current work going on looking at things like remission and relapse and other ways to define these kinds of things probabilistically. Okay, so that's it for today. Thank you. Yeah.
Thank you. It's really interesting. It looks to me like you tuned this to try and basically get, or you're looking for an F score as your evaluation. But I think if I was doing some research, I might want to maximize my positive predictive value because I want to get a clean cohort. How would I change your methods to do that?
Yeah, so you're, I guess you're mostly talking about the temporal aggregation portion here. And so, let's see. I think, so if you're, there are a lot of cases where positive predictive value might be more important. I think it's fairly easy to just report, like to train a different metric. You can just put it in as, yeah, if you're optimizing a particular parameter, you can just use that as a metric instead of F-score. So it shouldn't be an issue at all. But it is an interesting problem because there are probably a lot of problems within medical informatics that might be more interested in precision. Anyone else? Yeah.
This department for a few months, so I'm kind of still learning. But I have a quick question about Monte Carlo and Markov Monte Carlo simulation. Did you incorporate that somewhere in there, or is that something you're looking into the future to incorporate?
Yeah, so that kind of estimation was not necessary for these kinds of tests. The Markov random fields that I was using here are actually very simple to implement, and they basically end up being, like I said, phrases with weights on them. So it's this particular method we probably won't even need to try anything. It's, yeah, I don't think it'll be necessary for this. There might be other parts of this problem that we can tackle with, yeah.
So I just had a question. This was super interesting. I'm trying to follow most of it. One of the things I wonder is, how do you deal with the fact that your gold standard comparator isn't so gold, right? So oftentimes, what the clinical diagnosis for these patients is, even if a physician has said it, has treated them appropriately, there's some estimates that, and asthma is kind of a good poster child for this. Maybe 30% of those patients don't actually have asthma.
Yeah.
How do you deal with that?
Yeah, it's a really hard problem, and I think we deal with it in terms of when we're trying to train models. We deal with that by getting multiple people to look at the same thing, and even if it's not perfect, at least you have you have some set of data so that you can characterize how different are multiple people's opinions about this particular problem, and then that inter-annotator agreement, that kind of basically tells you this problem is this hard. You can really only expect humans to get 70% similarity, so you can't really expect a computer to do much better than that, right? So that's one thing that that has been done in order to address that kind of a problem. But it is a fundamental kind of problem, because even if you're looking at asthma or any of these other cohorts, there's going to be multiple criteria, recommendations, comprehensive review of the literature that have different recommendations and stuff like that. And I think it's an open problem. But the more, not standards, but the more attempts at defining those things that we have, the more that we can kind of layer those things up and use statistical methods to overcome some of the noise that's inherent in the problem. Bill?
Just to elaborate on that, there was, it's probably about maybe almost 20 years old now, but George Ripsack once, in the early days of NLP, did a study and basically was able to show the success of the NLP algorithm by showing that its distance of disagreement from multiple human users, and these were actually physicians, was actually, it was in that range of error. So to get absolute agreement is almost impossible. And another thing that we know from information retrieval systems evaluation is that when you evaluate systems using different relevance judgments, it, for the most part, doesn't matter. As long as you have a decent set of judgments, you can substitute in different judgments, and the relative performance of systems will be the same. So if a system does good with one set of judgments, it'll tend to do good with another. So the question is whether you want sort of this kind of absolute answer, which George Ripsack's work showed is very difficult, versus a relative answer.
Yeah. Other questions? Okay. Thanks. Cool. Thank you.